LPIC 101.2 boot the system. Armand Shahriarian. LPIC 101.2 boot the system. 101.2 Lesson 1. Introduction. In order to control the machine, the operating system's main component, the kernel, must be loaded by a program called a bootloader, which itself is loaded by a pre-installed firmware such as BIOS or UEFI. The bootloader can be customized to pass parameters to the kernel, such as which partition contains the root file system or in which mode the operating system should execute. Once loaded, the kernel continues the boot process, identifying and configuring the hardware. Lastly, the kernel calls the utility responsible for starting and managing the system's services. Note: on some Linux distributions, commands executed in this lesson may require root privileges. BIOS or UEFI. The procedures executed by x86 machines to run the bootloader are different whether they use BIOS or UEFI. The BIOS, short for Basic Input/Output System, is a program stored in a non-volatile memory chip attached to the motherboard, executed every time the computer is powered on. This type of program is called firmware, and its storage location is separate from the other storage devices the system may have. The BIOS assumes that the first 440 bytes in the first storage device following the order defined in the BIOS configuration utility are the first stage of the bootloader, also called bootstrap. The first 512 bytes of a storage device are named the MBR, master boot record, of storage devices using the standard DOS partition schema and, in addition to the first stage of the bootloader, contain the partition table. If the MBR does not contain the correct data, the system will not be able to boot, unless an alternative method is employed. Generally speaking, the pre-operating steps to boot a system equipped with BIOS are: 1. The power-on self-test process is executed to identify simple hardware failures as soon as the machine is powered on. 2. The BIOS activates the basic components to load the system, like video output, keyboard and storage media. 3. The BIOS loads the first stage of the bootloader from the MBR, the first 440 bytes of the first device, as defined in the BIOS configuration utility. 4. The first stage of the bootloader calls the second stage of the bootloader, responsible for presenting boot options and loading the kernel. The UEFI, short for Unified Extensible Firmware Interface, differs from BIOS in some key points. As the BIOS, the UEFI is also a firmware, but it can identify partitions and read many file systems found in them. The UEFI does not rely on the MBR, taking into account only the settings stored in its non-volatile memory, NVRAM, attached to the motherboard. These definitions indicate the location of the UEFI-compatible programs, called EFI applications, that will be executed automatically or called from a boot menu. EFI applications can be bootloaders, operating system selectors, tools for system diagnostics and repair, etc. They must be in a conventional storage device partition and in a compatible file system. The standard compatible file systems are FAT12, FAT16 and FAT32 for block devices and ISO 9660 for optical media. This approach allows for the implementation of much more sophisticated tools than those possible with BIOS. The partition containing the EFI applications is called the EFI system partition or just ESP. This partition must not be shared with other system file systems, like the root file system or user data file systems. The EFI directory in the ESP partition contains the applications pointed to by the entries saved in the NVRAM. Generally speaking, the pre-operating system boot steps on a system with UEFI are 1. The post-power-on self-test process is executed to identify simple hardware failures as soon as the machine is powered on. 2. The UEFI activates the basic components to load the system, like video output, keyboard and storage media. 3. UEFI's firmware reads the definitions stored in NVRAM to execute the predefined EFI application stored in the ESP partition's file system. Usually, the predefined EFI application is a bootloader. 4. If the predefined EFI application is a bootloader, it will load the kernel to start the operating system. The UEFI standard also supports a feature called Secure Boot, which only allows the execution of signed EFI applications, that is, EFI applications authorized by the hardware manufacturer. This feature increases the protection against malicious software, but can make it difficult to install operating systems not covered by the manufacturer's warranty. The bootloader. The most popular bootloader for Linux in the x86 architecture is GRUB, Grand Unified Bootloader. As soon as it is called by the BIOS or by the UEFI, GRUB displays a list of operating systems available to boot. Sometimes the list does not appear automatically, but it can be invoked by pressing Shift while GRUB is being called by BIOS. In UEFI systems, the ESC key should be used instead. From the GRUB menu it is possible to choose which one of the installed kernels should be loaded, and to pass new parameters to it. Most kernel parameters follow the pattern option equals value. Some of the most useful kernel parameters are ACPI enables/disables ACPI support. ACPI equals off will disable support for ACPI. Init sets an alternative system initiator. For example, init equals/bin/bash will set the bash shell as the initiator. This means that a shell session will start just after the kernel boot process. System.unit sets the system target to be activated. For example, system.unit equals graphical.target. System also accepts the numerical run levels as defined for SYSV. To activate the run level 1, for example, it is only necessary to include the number 1 or the letter S, short for single, as a kernel parameter. MEM sets the amount of available RAM for the system. This parameter is useful for virtual machines, so as to limit how much RAM will be available to each guest. Using MEM equals 512M will limit to 512 megabytes the amount of available RAM to a particular guest system. MaxPus limits the number of processors, or processor cores, visible to the system in symmetric multiprocessor machines. It is also useful for virtual machines. A value of 0 turns off the support for multiprocessor machines and has the same effect as the kernel parameter NOSMP. The parameter maxPus equals 2 will limit the number of processors available to the operating system to 2. Quiet hides most boot messages. VGA selects a video mode. The parameter VGA equals ESC will show a list of the available modes to choose from. Root sets the root partition, distinct from the one pre-configured in the bootloader. For example, root equals /dev/sda3. Root flags mount options for the root file system. RO makes the initial mount of the root file system read-only. RW allows writing in the root file system during initial mount. Changing the kernel parameters is not usually required, but it can be useful to detect and solve operating system-related problems. Kernel parameters must be added to the file /etc/default/grub in the line grub_command_line_Linux to make them persistent across reboots. A new configuration file for the bootloader must be generated every time /etc/default/grub changes, which is accomplished by the command grub-config-o/boot/grub/grub.cfg. Once the operating system is running, the kernel parameters used for loading the current session are available for reading in the file /proc/command line. Note: configuring grub will be discussed further in a later lesson.